Hello and welcome to this lesson on dynamics, which is part of the Forces in Motion module for OCR A-Level Physics. So in today's lesson on dynamics, we're going to understand the different types of forces and calculate the different forces. So if we've been successful and we've learnt in today's lesson, we should be able to state the different types of forces such as tension, the normal contact force and upthrust. Draw free body diagrams for situations and calculate the resultant force in different situations. So in today's lesson we're going to look at 3.2.1 dynamics of OCR A-Level Physics. Now in many situations you need to be aware of the different forces acting on a body. Now some of these forces you need to be aware of include weight, which is the gravitational force acting on an object through its centre of mass, which we can calculate with the equation weight equals mass times by gravity, where on Earth the gravitational field strength at the surface is 9.81 meters per second squared. We have friction, which is the force that arises when two surfaces rub against each other. We have drag or air resistance, which is the resistive force on an object travelling through a fluid. We have tension, the force within a stretched cable or rope. We have upthrust, an upwards buoyancy force acting on an object when it's immersed in a fluid. And we have the normal contact or the reaction force, which is a force arising when one object rests against another object. Now this force comes from Newton's third law of motion, and this force always acts perpendicular to the surface. Now all forces are measured in newtons. Now 1 newton is defined as the force that will give a mass of 1 kilogram and acceleration of 1 meter per second squared. So 1 newton equals 1 kilogram meter per second squared. Now to fully understand the forces acting on an object, we must draw a free body diagram of that object. Now a free body diagram should be drawn like a scale diagram. The length of the arrow should represent the magnitude of the force, and the angle of the arrow should represent the direction the force acts. Now the arrow should always start at the centre of mass of an object, as shown on the diagram on the screen. Now to understand this, a free body diagram shows a single body on its own. This diagram should include all forces that act on the body, but not the forces it exerts on the rest of the world. And the free body diagram shows the resultant force acting on the body as a result of the different forces. But the free body diagram does not explicitly show the resultant force itself. Now, as forces are vector quantities, the arrow labels of the forces should show the size and the direction of the forces, as shown in the following situation of a satellite, and the next situation of a parachutist, or the next situation of a car. Now, if we consider the example of a human standing up, we can see our free body diagram. Now, as we know the human is in equilibrium, the forces must be equal to each other. So the upward forces equal the downward forces, or in this case, R will equal W. Now when an object is in equilibrium, there is no resultant vector or force on the object. This means if drawn correctly, the free body diagram for a body in equilibrium should form an enclosed shape when arranged into a scale diagram. Now a scale diagram is when the vectors are placed head to tail in a scaled size to each other. So in this example, if the spider is hanging in equilibrium, then when the forces are arranged as a scale diagram head to tail, they should form an enclosed shape, as shown here. Now, an object in equilibrium can either be at rest or moving with constant velocity. Now, when objects are not in equilibrium, there is a resultant force on the object. The resultant force acting on the object will cause the object to accelerate. And we can work out the size of the resultant force, as resultant force is the inertial mass times by the acceleration, or F will equal ma. Now, if the resultant force is in the same direction as the motion of an object, the acceleration is positive. If the resultant force is in the opposite direction to the motion of the object, the acceleration is negative. Now, when objects are in equilibrium, we have said before there are no resultant forces on the object. So we can say that the overall horizontal forces equal 0, and the overall vertical forces equal 0. So if an object is in equilibrium, the sum of the components in each direction, horizontal or vertical, must equal to 0. So if it's in equilibrium, we can say that R minus W equals 0, which allows us to rewrite it as R is equal to W. In this example here, if our object's in equilibrium, we can say that T minus D equals 0, which we can rearrange to say T equals D. Now, when asking to calculate a force on an object in equilibrium, you must carry out the following procedure. The first step is to draw the free body diagram of the object. The second step is to identify the forces acting in just the horizontal or the vertical. The third step is to identify the forces acting at an angle and resolve these forces into horizontal and vertical components. You would then balance the horizontal and vertical forces on the object to find the desired force you require. Now, an example of this is as follows. A child of weight W on a swing set is at rest due to the swing set being pulled to the side by a horizontal force F1. The rope supporting the seat is at an angle theta, and assume the child is at equilibrium and the seat has no weight. Write an equation for theta. So the first step is to identify the forces in either the horizontal or the vertical. So F1 is in the horizontal and W is in the vertical. The next step is to identify the forces at an angle and then resolve them into horizontal and vertical components. So T is at an angle, so it must be at the vertical and it must be in the horizontal. Now, the sine and cosine values for the horizontal and vertical components of T have been reversed, as the angle measured has also been reversed from the horizontal because it's coming from the vertical. So therefore we can say the vertical component is T cos theta, and then the horizontal component is T sine theta. You can do that by drawing out your triangle and using your trigonometric identities for sine and cosine. The third step is to equate the horizontal and vertical components. So we can say horizontally that F1 minus T sine theta, because they're in opposite directions, is equal to 0. And then vertically, W minus T cos theta is equal to 0. We can then rearrange them to say horizontally F1 is equal to T sine theta, and vertically W is equal to T cos theta. So if we then use that to work out our value of theta, we know that sine divided by cosine is equal to tan. So tan theta equals sine theta over cos theta. So F1 over W is equal to T sine theta over T cos theta. The T's will cancel through and sine over cos becomes tan. So F1 over W equals tan theta. So arctan of F1 over W is equal to theta. And there we've answered our question. So to summarise what we've looked at in today's lesson, the net force or resultant force is equal to mass times acceleration, F equals ma. The Newton as a unit of force, then the weight of the object is equal to W equals mg. The terms tension, normal contact force, upthrust and friction, free body diagrams, and one-dimensional and two-dimensional motion under a constant force. So if we've been successful and we've learnt in today's lesson, we should be able to state the different types of force such as tension, normal contact force and upthrust, draw free body diagrams of different situations, and calculate the resultant force in different situations. So thank you so much for watching this lesson on dynamics, which is part of the Forces and Motion module in OCR A-Level Physics. Thank you so much and have a lovely day.